Very good. So what we were looking for was we were trying to get this spreadsheet to be nailed down. I decided to offline. I looked at this spreadsheet a little bit more to understand it. And so I'm going to walk you through how I nailed down these numbers, this number set. The final result of all these numbers, I was trying to get it to something, our final speeds to a respectable number. For instance, 6 feet per second, which is still fast for low gear, and 13 feet per second. That's going to be very, very, very quick, but speed is a very important aspect to this game. I would recommend for visualizing the speed, getting out a tape measure and laying it down on the ground and have a timer and imagine how fast it's going to be going. Visualize the rate so you can imagine how fast a robot's going to go. Even get out a whole old drivetrain. Actually, this is better. Get out an old drivetrain that already works and clock it. Figure out how fast it goes and how comfortable you are as a human driving a robot going super fast. Getting some emotion into these numbers. Are you scared of 13.7? We might find that gearing for 11 feet per second is going to give us a better torque to speed ratio, and it's better if we can really know what numbers we're shooting for. But since I don't have a robot on hand, 6 and 13, that's I think in my brain a pretty good first at the get-go estimate. So 6 and 13 feet per second, very good. That's what we're looking at. I punched in our wheel diameter as 4. A target acceleration, that's something else that you're going to have to measure off of a real robot and get a sense for some good accelerations, but I put this at 12 for these calculations. Robot weight at 100. You know, as I'm thinking about this, the robot weight is going to be a little bit more. We've got 120 pound weight limit, and then we've got batteries and bumpers. So you can put quite a bit of weight down for those, maybe 30 pounds. So at the total, our sum might be 150. Some of these numbers might be 150 pounds if we max out all of our robot weight. So let's imagine that our robot is actually going to be carrying our battery and carrying the bumpers, which means that it might be closer to maybe the 135 pound mark, assuming we're under speed or underweight. So we can see that that's kind of odd. I think there might be something wrong with these calculations because the final speed didn't change, the torque changed. Actually, the final torque didn't change. So something is wrong with these calculations. I'm not exactly sure what it is. You might want to recreate this kind of spreadsheet because there's something wrong with it. Recreate this over the summer, but just for this demonstration, I will just use these numbers. I'm scanning through all of these so that you can see what equations I have set up. And you're going to want these too. This is some more numbers that I had filled out before. And yep. Okay. So you can recreate this spreadsheet now, fix it, and use it for yourself. Now, there was a big error that I had not noticed in the last part, which was these torque per sims at the amperage. That's what we use motor curves for. The more current that we put inside the motor, the stronger it's going to be. And it's going to change how our motor behaves. So if we jump into the internet we have this handy motor curves spreadsheet. And if we load up the sim, we can see this is the output. The output power is here, this parabola power loss. What we're really looking for is the current, and it looks like it's this linear red line that just keeps going up and up. So that is the slope that we're really looking at. And what this graph really tells us is the more current you put in, how much torque are you getting out. We don't have to read directly from that graph though. This is computer generated, so we can get an estimate. The computer will estimate from the graph. So if we put 20 amps in to one single sim motor, we'll get 0.32 Newton meters out, or 0.233 foot-pounds at 4619 RPM. So I took those two numbers at 20 amps and however many volts, 12 volts, and I plugged it into here, 0.23, 4620, and that shaped our speed and torque, which should help shape this final number. Now the other thing, give and take, is figuring out the sprocket ratios, the gear ratios and everything. These spreads, again, are the difference in shifting between low gear and high gear, the ratio between low gear and high gear. So if we use this 2.1 spread, high gear will go 2.16 times faster than low gear. However, these spreads are different depending on what gearbox you use. So for instance, let me go back to Vex Robotics. I don't have that tab up anymore. I just want to show you what I mean by depending on what you use, what I mean by that. So when you go and you look at the gearboxes, you can get this 3-sim ball shifter, and what this does, this has configurable reduction in shifter spread options. So you can change what spread, the ratio between high gear and low gear. But down here, the 2-sim ball shifter has a fixed spread. So you have only one choice for the difference between high gear and low gear. You can still put it at a third stage gear stage on there, but you know, that's not changing the ratio between the high gear and low gear. So what I did is I looked through this entire chart, and I picked gear ratios that seemed to fit what I wanted to have us do. So this 917 and 2083, I plugged those. I'm sorry, no, these 1173 and 2667. I plugged those up there, so I'm using the 64 to 20 gear ratio, and then I also used sprocket gear down. I geared it down even further beyond this gearbox using sprockets. Before it even touched the wheels, it got geared down more, and then it spits out these values, which inherently are probably wrong. Let me show you what I mean by the sprocket ratio and the gear ratio. So I whipped this drawing up. These blue ones here are wheels. This dark gray one is the output shaft. This is what the motors are turning. The gearbox is behind this. It's powering that shaft. So you can imagine that as being the gearbox, right? So that's where all the power is being converted from the motors. It's being slowed down significantly here, spit out at this shaft, and then it's being slowed down even more between these yellow sprockets and these blue sprockets. Now, the small to the big means these are going to be, each one of these wheels are going to be spinning slower than this, which means we get more torque, less speed, which is good for pushing. And we're already going freaky fast because our sim setup is insane. Each one of these guys, these lines represent chain, And you can see this layout needs to be very carefully thought through. Just as a side note, this is only half the robot. There would be this exact same thing mirrored on the other side, of course. That way we could actually go forward and turn. Anyway, we have to very carefully understand the how we're going to lay out these sprockets. This is a very standard way of doing it, of putting 2 sprockets on the output shaft of your gearbox, running one to the right, one to the left, and then kind of daisy chaining this wheel to that wheel. So this wheel is driven by that, which is driven by this, which also drives this, which also drives that. So you can see how they have that relationship. If this chain breaks, this one chain breaks, both these wheels don't move, but they move together. These 2 wheels move together. So you can see how that mechanically be tied together. But what this lets us do is it lets us use minimal amount of sprockets, almost nesting the sprockets together. And the sprockets can't have more than 1 loop of chain on them. You have to only 1 sprocket can handle 1 loop of chain. So this just lets us use the minimal amount of sprockets, simplicity, making sure it's as simple as possible, as light and easy to service. So let's CAD this arrangement with these numbers, with this hardware and these sprockets. Let's put all of that inside our robot here. We've laid out already where the wheels are going to go, which is a good thing. So let's go ahead and download the CAD models for the wheels. We could CAD every single one of the components that we're going to use. However, what's really great about these websites here, using First Robotics suppliers and many other suppliers too, like McMaster-Carr or SDP-SI, they give you CAD models of the actual part, very detailed too. So you can see up here with CAD models right next to Docs and Downloads, you can get the 2-stage with Grayhill encoder entire box, and you can also get the 3-stage version. We have specified the 3-stage version, the 6024. So we would download that step file. I've already done so, and it's already inside the GrabCAD CAD library, RatPack library. It's already in there. So what I will do is I'm just going to insert an existing component. I'm going to browse inside our RatPack library for a gearbox that is this 6024, 2-sim gearbox, 3-stage. Actually, hold on a second. Simplicity-wise, that one was added in error. This gearbox is just the generic. The previous one had a specific gearbox gear ratio, and all the other parts were deleted. But this has every single gear stage. I have shown, let me just open this up so you can see what I'm talking about. Here it is. When you open this, a downloaded CAD model, if you download a CAD model and it comes in an assembly, you can save it as a part, and then it'll convert all of these surfaces into, to, instead of having them be parts, just individual surfaces, which is very, very nice. It lets you take complex assembly and refer to it as just a part. Okay. So what you'll notice is that there are gears inside of gears here. So if I hide this gear, oh goodness. Oh, they were hidden before. But there are gears inside of gears. It's not like that mechanically in the actual model, but what it does is it lets us swap out the gear ratios inside the CAD model and custom tune it to whatever assembly that we're using. So currently this is the 20T tooth, and the 64 T-tooth. And that's that. So you can swap out what gears you want to use. For instance, if you wanted the 34, you can show the 34 tooth, and it will pop it in your CAD model, and you don't have to change anything. You can see this lets you better make your assembly have greater detail. But I'm happy with this. These also come with a bracket down here. I've hidden the bracket. The bracket is used for mounting it to a flat surface, but we have a frame plate that we're using, and that frame plate is what we'll use to, we're going to mount it using this front face, mount that face directly to the frame plate, so those things will be coincident. Then, for simplicity's sake, we're going to take the right plane of this assembly, and we're just going to make that to the front plane of our robot. That way it's centered, left and right, forward and backward, I guess. And then the next thing is determining the height. How high do we want this to be? So for that, I have constructed a plane that goes between the highest point of the let me open the part so you can see how I defined it. So this plane goes through the center of the part from this tippy top point of the plane of the gear to this very bottom tangent part. And all I did to do that was I made a sketch of a line that went from the highest point to the lowest point, made those things coincident, and I added midpoint, just a point at the center, and then I added a plane, a reference geometry plane. Went to features, reference geometry plane, and I added this guy, which takes the top plane, makes it parallel and coincident to that point, that midpoint, and it places a plane right through the center of our part. And so I can use that to locate it up and down. So I'll take that new plane that I created. Oops, that was a sketch. New plane, and the top plane of one of these parts. I want to do it to this one. Now, what I noticed I did was something a little bit silly, which was I took this gearbox and I actually mated it to the mirrored side. It's best practice to mate everything to a dominant side of the robot. As long as it's symmetrical. If it's going to be symmetrical in the end, mate all new components to a dominant side of the robot. That way you don't have components floating in space on the left. It's harder to as the assemblies get more complicated. This makes your life much, much easier. So what I'm going to do, since I already mated this fully in place, it's already fully defined, just going to modify some of the mates that I added. So for instance, this is no longer going to be true. It's not actually going to be mated to that face. It's going to be mated to this face, like that. If I flip the alignment, that's not doing any favors. I'm gonna I'll explain why you saw that shaft extrude extremely far. That's an odd behavior, and I'll show you how that happened. Parallel. I'm gonna flip this parallel. Whoops. Whoa, that was not my intention. Undid that. I think I did. There we go. That's better. Or is it not better? Did I mess it up or not? Okay, yeah, it's back now. Very good. It's this. Yeah, by doing that, I think I actually broke something. Or is it fine? I'm rebuilding. Oh yeah, that's fine. I just needed to rebuild the document. That constraint, this constraint, and that constraint. So this one I'm going to flip. Nope. I tried that before, just in a different spot. What if I flip this one? There we go. That did what I wanted. So now the shaft, this is where the shaft comes out. It will be there. Now, what I did, you know what? This is a part that I've worked with before. So what I'm going to do is I'm going to, oh, I can't. I deleted it. Okay, never mind. I thought I could. I thought I could show you something, but I can't. So we're going to do blind, and so this has a shaft that is somewhere around this length, right? It's a hex shaft, and it looks like that. It's actually significantly longer. I don't remember how long it is. Let's just take a look in the model. The model comes with a shaft already inside of it. If you get the long shaft, which is what we're going for, maybe if we do I want to know how long the shaft is so I can put it in the CAD model. Well, I don't think they tell you here. This is just assembly. Well, the shaft is long. Not quite that long. That long. All right. That's just for representation purposes for now. Great. So we've got lots of space here, plenty of space for a wheel. It's actually somewhere around here, I think. I think it's 5 inches long. Now that I see it in the context of a robot. Very good. So let's take on the next part of our drivetrain. And the next part of the drivetrain is going to be figuring out these wheels. I'm going to show you a really cool trick. It looks like we're going to have to create 3 different arrangements of wheels. What we're going to end up doing is we're going to create a subassembly. We're going to create a new assembly, insert a wheel, insert a shaft, insert these bearings. I'm sorry, these sprockets. And we could make a subassembly, this one subassembly, and then this is the same subassembly as this one. This is different than this, right? It doesn't have this extra one. So we could save this assembly as and delete this part and then insert it. Or there's a better way of doing it, and it's called configurations, where you can use one assembly like this and turn on and off components in specific instances in a major assembly. If you didn't follow that, don't worry about it. We're going to take a look. We're going to create it so you can really see. You'll get a sense for it once we start working with it. Great. So what we're going to do is going to create a new assembly. This assembly is going to hold a few parts. It's going to hold the wheel, the shaft, and 2 sprockets. We're going to make this one, the one that has the most parts in it. And let's go ahead and browse for those components. I believe they're all in the Rat Pack library. So we'll go to wheels, the performance wheel, and performance foreign checks. There it is. I'm going to float this. I see that this is like laying down on the table, as if, so top plane's there, as if the top plane's the tabletop surface. I like to orient this always as if it's on the robot already. So what I'm going to do is I'm going to lean it up. So I'm going to take the top plane and make it to the right plane so it stands it up. I think this is going to be flipped. I'm not entirely sure. And then top plane on the right plane, maybe. Flatten that out. And then lastly, front plane on. Front planes are shared. So there you go. You can see how that wheel's in there. It's important to note if you download a new one of these wheels, it doesn't come with this tread. What a really cool thing that you can do with new downloaded models, this is what you'll see in a downloaded model. You can actually you can add to the model your own geometry. So you can always add to it. It's hard to, we'll cover that. So what I would do here to add the tread, because currently the outer rim diameter is 3.7 inches. The tread makes this a 4-inch wheel. It doesn't get to 4 inches until you add the tread. So I did a revolve extrude on a sketch that was on the right plane, and the sketch is of a rectangle that looks like the silhouette of the tread. It's 0.2 inches thick, and it's revolving around that line. It just revolves all the way around. You're taking that one rectangle and sweeping it across the entire thing and adding material as you go. And now you can see the outer diameter of this wheel is indeed 4 inches, just like we had intended. So we'll go back to our subassembly here. Let's add some more parts. Next, we want to add our mechanical sprockets and our 32T sprocket. This is the sprocket set that we're using on the subassembly. That'll be these two yellow or blue sprockets, and we had calculated that we wanted this 32 and 16 ratio. That'll get us to could have done that in my head, couldn't I? Half. So one, as every rotation the gearbox makes, the gearbox output shaft, the wheel will take a half rotation. So it slows it down 2 to 1. Now, we're going to take this, we're going to make that concentric so that this is centered on the wheel. We're going to lock the rotation by making one of these holes concentric with one of those holes. And you can see we can set it as close as we want to the wheel itself. But we don't want to get too close because chain has thickness. Let's figure out how thick the chain actually is. Just as a good resource for you, McMaster-Carr has fantastic documentation on a whole bunch of mechanical solutions. You can just see all of the things that they have. It's almost endless. But if you don't know what something is called and you're just trying to figure out figure something out, this is a great place to browse through their library, and you can find things really fast. Anyway, we're looking for roller chain. 25 roller chain. 25, we're only working with speed, not too much with torque in this game, so we're probably not going to be popping any 25 chain anytime soon. We're just going to, if we were really in big push matches, we could upgrade it to a 35 chain. But you can see here with 25 chain, McMaster has a SolidWorks document that you can download of these few chain lengths, and you can get critical dimensions, like the width of the chain from pin end to pin end is 0.3 inches. So whatever we do, we want to make sure that our chain, which is 0.3 inches, is never going to rub up against the aluminum wheel like that. If it gets too close, even though it might not, technically this isn't rubbing up against it, that would be, we have to have some sort of assembly tolerance. Luckily for us, we don't have to think too much about that, because the lovely people at Vex have already done a fantastic job, and they have created things called Versa hubs. I don't have them logged correctly, they're just under hubs. But let's take a look at these Versa spacers, half-inch, or not half-inch, that's a lie. Browse, I want the quarter-inch one. Half-inch one you can use for 35 chain, quarter-inch one you can use for 25 chain. So these are injection molded parts, plastic pieces, and their entire function is to be a spacer. So what you do is you make it concentric with your thing, and you can see the hole pattern. Sprockets have a receiving pattern for this peg, and these pegs fit perfectly inside, and it's got the hole pattern that lines up and everything. So what we can use this for, I'm just going to constrain this into space here for just a couple. There we go. So how we can use this is as a spacer between the sprocket itself and the wheel. So instead of cutting 6 individual spacers that may or may not be the same length and we get a wobbly sprocket, we can simply place this directly onto our wheel. Push it in as far as it can go, and we get proper spacing and then some for our chain. So for instance, if we wanted to see the width of our chain again, 0.3 inch chain. If it's centered on the sprocket just like that, we've got plenty of room over there. It's nice. These hubs, they save you a lot of effort, a lot of grief. Very good. Now, these are going to, this subassembly needs 2 sprockets. So what we'll do is, let's just do a linear pattern. We want to take the direction of going this way. That it's just generally that's the direction that we're going. We're patterning this and that, and we're having 2 instances. The space between them, between pattern, should be, shouldn't that just be half inch, quarter inch? I'm sorry. Yeah, quarter inch. Right? Or is that not right? No, that's wrong. Looks like it might be 3/8. Something like that. It's fairly close. What we can do to firm that number up is take the distance between the inside edge and the inside edges of these two, and we see that the distance between them still is 0.15 inches too big. So I'll just come back to this pattern, subtract 0.15 inches, and it's 0.225. But that was 0.015, not 0.15. My bad. Yep, that's a slight difference. Minus 0.015, not 0.15. That's better, 0.36. And now you can see that it's just touching. Holes go all the way through. Look at that. That's 2. So the only thing that's left is to make, well, let's just jump back over to our illustration. Now we have our wheel, 2 sprockets. We're not going to worry about the chain, especially not in the subassembly. If we were to add chain, that would be in the full robot assembly. And then the last thing we need to put in is this as the shaft that holds it all together. So what we're going to do is we're going to insert a new component, insert component, new part. And again, if we're inserting a new component, it's asking us what plane do you want to start sketching on. And the right plane is going to be a good one to sketch. And I don't want to make any references on this, and I'm going to say that's horizontal, and this is 1/2 inch in diameter. I'm going to set the inches. Perfect. And take that sketch that I just made, extrude it to be, I don't know how long that's going to be, so how about just 5 inches for now. I just realized I made a goofy mistake. I constrained it over here in space, but forgot to do the critical point because I was changing units. Just brain fart. Forgot to make the this thing on the origin. There we go. So now take a look at this. Look at that. There's a shaft that gets the job done. We're going to run into a couple of things as we're putting this robot together. But for right now, let's just keep this the way it is. So we're going to come back and we're going to modify this shaft a bit. I'm going to name that shaft while I'm at it here. I'm going to name this axle. And since I'm doing the naming scheme of custom parts have DT, if they're in the drivetrain, I'm just going to add that custom naming scheme. And let's go ahead and save everything. Now I have to save this entire subassembly. So I'm going to jump out to CAD Lab, put it in advanced, and we're going to say this is DT wheel sub. And the part that we inserted, I want to make sure that that is saved externally as DT wheel axle, which is what I just named it over there. And it's going to be saving in the last place. It's going to be saving right next to it. So we'll hit OK. This goes from assembly 1 to DT wheel sub. Great, let's go back to our full robot assembly. And let's insert it. Insert that new wheel subassembly. Here it is. Here's our wheel subassembly. Looks like I made that in backwards on the plane. You could just over here flip it in this orientation, but it's cleaner for me to understand how things are mated if I just simply flip that mate alignment. And while I'm at it, I'll just reverse that thickness just to get things going. Cool. There it is. What I've done is I just moved it to the other side. There it is. So what I want to do is I want to have this hole here is going to be a clearance hole for a 1/4 bolt. A bolt is going to fit inside this hole, and it's going to thread into the end of this shaft. So what we're going to do is we're going to make a hole inside this shaft on either end. Make a hole. That's a circle. And extrude that. Oops, that's a positive extrude. That's adding material. I want to take material away. Extrude that through maybe 1.5 inches. That would give us room for a 1 1/4 inch long bolt, which should hold the wheel on. Then I'm going to mirror that hole to the other side, and I'm going to need a plane that goes in the middle of my part. So I'm going to put that there, and take this, mirror it across that. There we go. Look at that. We got a hole on both sides now. So I can mate that hole to that hole. So now they're concentric, and the wheel, let's see, is lined up with the sketch that I've made before, because the hole that I just mated concentric to inside this plate, that location of the hole was defined to this master sketch. So because the shaft was mated concentric with the hole, and the shaft is concentric, and the wheel is concentric to the shaft, the wheel is going to be concentric with everything. And it all lines up. Everything is concentric with each other, making sure all those logic streams are in place. Now, the only thing is this can move in and out, and it can also still spin. So to take care of those things, let's just take the top plane of this and mate it parallel to the top plane of the assembly. That keeps it from spinning. And we'll take this front face, and we'll mate it so that it touches. It's being clamped up against the inside face of that. So you can see how it locks it inside inside of our robot drivetrain. Very good. But uh-oh, we got interferences. You can see how the wheel is crashing in to our edge flanges here and this gusset. So we're going to have to modify those in a bit. But we can solve one of these interferences with this by moving the wheel inwards, closer to the inside of our robot. So let's do that. So relatively, by moving the wheel closer to the inside of or closer to the center of the shaft, we're in effect, we're taking this end of the shaft and we're extending it longer. You can kind of see how relatively this face is getting farther away from that face. Reason why I'm bringing that up is this wheel isn't going to move across. This is centered on our work planes, on our assembly planes, and this is not moving. This is the thing. The wheel is constraining everything else. So what we're going to do is we're going to move the shaft left instead of moving the wheel right. Now the shaft is extruded this way, so we can add a second direction and just say 1.5 inches is good. I think that's a good number. So if it was 1.5 inches on the left-hand side, you can see how that'll push our wheel away from the edge. So that's very nice. Now it's quite a bit of space, but I think that'll be good for us. That'll make sure that there's plenty of space. Now we also want this face to mate to that face. Currently there's 1 1/8 distance between them. If we tried to mate these two together, it would try to push this plate outwards or it would try to squish the shaft together. But the plate's already fully defined and the shaft is already fully defined. So we're going to need to change the length of the shaft. But when we zoom out a bit and we think about the problem in general terms, hold on, let's see. There's actually a better way of showing you why this is important. Let's edit this, bear with me for just a second, and edit this mirror. Let's just mirror that gearbox to the other side. Yep, just what I thought. Look at that. Look how close our sims are to each other. In fact, they are interfering with each other. So currently, this is not buildable. We're going to need to move these two gearboxes closer to the ends, to the edges of our drivetrain, because this is not going to package. So in effect, what we really need to do is get this frame plate. The real problem is to get this frame plate as close to the wheel as possible, or as close to the sprockets, really, is minimize the distance between the sprocket and the wheel and the frame edge. So the way we've constrained it is that the frame is actually constrained location-wise with this top-down sketch. So you can see here there's this this line here. That line represents the inside edge of our represents that face. That line represents this face. So if we move this line closer to the left, if we move that line closer to the left, it'll modify the spacing of the three-dimensional part. How much? So we could go in here. Currently, it's over here. Currently, this line, this part here, we want to bring to the right, and it's arbitrarily set at 5.5 inches. We could set that to 3 inches if we wanted to. It'll bring this over, and you'll see here this plate is going to update. Moves over. Oh, but that's definitely not enough space. That's not enough space for this. We're going to need to make sure that we find some sort of magical number. So let's figure out what that magical number is going to be. So in a sense, the magical number is going to be the length of this shaft. Because the length of that shaft is going to define the distance between these two plates. So let's jump into this plate here, into our subassembly. Now, what's the shortest length we could make this shaft? The answer to that is, well, we could take off a little bit of length over here on this side. Maybe instead of 1 inch, make it 1 1/4. And then on this side, instead of making it arbitrarily 5 inches, we could do an offset from surface and say go beyond that surface by maybe 2 inches. Like that. So now you can see here, this to that, that's 2 inches away. if our sprocket, if we decide to add a third sprocket, we'd need to make sure that this face is always 2 inches away from the outermost sprocket. So now the length of this is 5.07 inches. That is the magic number that we've been looking for this entire time. So what we could do is we have 5.07. That's the length of this thing. We could go over here. We could edit this sketch, and we could say this 2 inches that we set before, or 3 inches, is going to equal 5.07. There's a downside to this way of what if something changes in the future? What if it no longer is 5.07? What if it needs to change and we forget to modify this number again? We can make this parametric, meaning that the distance here is going to be dependent on something else, dependent on another variable. So bear with me here and just follow what I do. What we're trying to do is get the length of this part into this sketch. So what we're going to do is create just a smart dimension that's not even in a sketch. Just create a smart dimension. It's 3-dimensional. And that gives us this read-only. You can't edit it. This is just an annotation, 5.07. It's going to tell us how big it's going to be. For instance, if we wanted to change this to 1.5 on this side, it's now 4.57. So that's good. And then we're going to create an equation. Global variable, this is going to be axle length. That's going to be a variable. And it's going to equal whatever that number is. So if this number changes, then axle length variable will change. So back in our assembly, what you'll find is that inside of our wheel subassembly, inside there is now an equations folder, and there's axle length, 4.57 inches, that new number that we've defined. This is the variable that we can reference. For instance, if we go into the sketch now, this 3 inches is no longer going to be an arbitrary 3 inches. It's going to be a very specific whatever axle length equals. So we're just going to say equals, create an equation, so we'll always look at this. I had no external references checked. But now what it's going to do is it's going to take this, whatever this axle length equals, and it's going to push that number to this sketch. So now you can see 4.57 appears here too. And now there's going to be a center distance, or the distance between the frame plates is going to be 4.57 inches. They've moved. Uh-oh. Looks like we're poking through. So that means that we need to, something's off a little bit. You can see here that the inside, between the inside plates, it's 4.445 inches. No, the reason that is, that's because it's the way this is defined here. 4.57 is from the outside edge of the robot to the outside edge of this aluminum. So that means that there are 2 thicknesses of frame plate that it's subtracting from this number to get to the inside width. So what we really need to do is compensate for that and just say twice the thickness of one plate, or 0.125 inches plus 0.125 inches plus the axle length. That increases this number a little bit. But what you'll find So after it updates, that the inside distance, that's what's really important. This equals 4.57 now. We just have to, this is what we were after in the entire time, getting this distance to be 4.57. We just had to jump through a hoop in order to get that to happen. That's all how you, that depends on how you set up your file. So now, look at that, it's no longer poking through. It was poking through 1/8 of an inch before, but now it's not. Now the really neat thing about this is that there's a hierarchy of what's most important. What's most important is that there is 1.5 inches between the edge of this sprocket and the edge of the shaft, and 1.25 inches from the edge of the wheel to the edge of the shaft. That defines the center, and that defines the distance between these plates. So that's a really cool, you can see how the hierarchy there of what's most important comes really into play. So now we can just double check how much space do we have between the wheel edge. We've got 0.3125 inches, and I think that's a good number. But we've got one more interference, and this is a very tight area up here too. We're going to have to get rid of that. Let's take care of that first. That's easy. Let's move the wheel to the right a bit so that it's not so close to the wheel, to the frame edge. We can accomplish that fairly quickly by opening up our sketch, our side profile view sketch. In all of its magnificent complexity and simplicity and elegance. Currently, I have a distance here, this 1 inch distance, from the tip of the left tip of the wheel to the outside of the frame is 1 inch. But that's not exactly what I'm talking about here. What I'm more looking at is I'm looking for a point that that intersects with this line here. That line is the upper edge of that bottom plate. That same line extends to what this is super close to. So if I take both of those things, what you'll see is this line actually skewers the sketch plane. It's perpendicular to the sketch plane. So there's the sketch and there's the line. You can see how that's going between it. We've got this point placed in on the sketch plane, and there's no coincident. You can't make this and that coincident because your SolidWorks is projecting this line, and it doesn't even see a point. But what you can do is you can make pierce. And what pierce is going to do is it's going to move that point until it intersects with the line at the sketch plane. So now that point is on the sketch plane and on that line at the same time. So that's what the pierce function does. And so we can see for sure now that this is very, very close. So I still want a 1 inch away from the between the wheel and that point. This is the point that I'm trying to space our wheel against, out of, away from. So I'm going to take this smart dimension. It's no longer going to be from the edge of the outside of the part. It's going to be to that point that we just defined. Oh goodness. Let me make that. Let me make a new smart dimension. I'm going to bring this wheel inwards a bit. I'm going to also bring this point down so that intersects, so that's coincident with the bottom plate, or essentially horizontal with this point here. That way, the closest the wheel is ever going to get to that edge is going to be whatever the smart dimension is. And we'll just call it 1 inch. Goodness, my computer is getting slow. That's all well and good. We will call that a day. So what we've done there is we've just very smartly defined where the wheel is going to be left and right relative to that edge of our frame. Look at that, everything is updated. We can see that the wheel hole and everything has changed. Everything is updated and it's super nice. Great. Now the next thing, this is going to be a little bit more tricky. This gusset here needs to go away. It's not worth trying to figure out some fancy geometry to get the wheel and the gusset to live peacefully next to each other. The gusset's just going to go away. It'll survive. We've got gussets all everywhere else, including on the top. So we just want to get rid of this bottom gusset, that bottom triangular bar. So let's open up that part. And I believe that's going to be on the mirrored side. So that's the actual edge flange, and this is the mirror. So we're going to want to modify, we're trying to get rid of this gusset and that gusset together. So I'm going to make a new sketch. And I'm going to take a rectangle. Just going to pop a rectangle on there. Like that. There we go. And I'm going to extrude that. Actually, you know, before I extrude it, I'm going to mirror that to the other side in the sketch. Mirror everything over there about this. There it is. Now I'm going to extrude cut that. Not going to go all the way through. Going all the way through would cut this one away too, which is not what we want to do. But instead what you can do is do a blind cut and link it to the thickness. That way it'll just cut through the thickness length. There it is. It's gone. I noticed that this, oh gosh, pivoting around is weird, that this fillet got a little bit funky. That's because we chopped away a significant portion of the fillet. So you can see there the fillet was there, and then we chopped part of it away. So what I'm going to do is I'm going to take that fillet, same fillet, and I'm just going to drop it underneath. Oh, can I not drop it underneath that? Okay. What we're going to do is we're going to deselect the things that, the edges that we've disappeared, the edges that we've destroyed with the cut extrude, because it won't let us rearrange this. Rearrange the fillet to go underneath unless those edges are no longer externally referenced. Chicken and the egg thing. Or I guess it's not that at all, actually. Very clear which one came first. Oh, this is referencing the fillet. Well, I guess we had to do that anyway, but just joking. What I was explaining before didn't exist. I made a constant to the fillet to define the length of that, and it really just needs to go to that point now that the fillet's not there. Now we can bring the fillet underneath, which means we can fillet these new edges that we've created with the cut extrude. Then we'll come over here. Just like that. Very nice. Now when we look in our subassembly or in our full assembly, look at that. Our wheel is now free and clear of any objects that might get in the way of it turning. As I say that, though, there is one big issue with this wheel subassembly so far. That issue is this this bar here, this our axle, is not going to turn. Its purpose in life is to not turn. It's just there as a stabilizer to hold onto the wheel. It's just the axle. It doesn't spin. But the wheel we chose mounts rigidly to the axle and it expects it to turn. The result is that the wheel is not going to turn very easily. So what we're going to do is I chose the wrong wheel. AndyMark makes another kind of wheel that doesn't have a hex bore. It has a round bore that is designed for a bearing. So we'll put a bearing, a wheel that can receive a bearing on here instead. Now I have that already in my CAD library, the RatPack CAD library. But so I need to essentially replace this wheel with a different part. I don't have to delete it though, because then I don't, because deleting, which means I would have to insert a new component and re-add all of the mates I put on attached to it. Instead, I can just replace it with File, Replace. Say I want to replace this component with just the regular 4-inch wheel, and say check. And it's going to try to reattach all of the mates again. And it's going to say it's looking for this edge here, this round edge. This is the old part, the one with the hex, and this is the new part, the one with the bore, with the hex bearing. So it's saying what face is this face? That face is that face. What face is that face? That face is that face. What face is that face? That face is that face. And it just attached all of the mates again. And I didn't have to do hardly any work. Now it looks like the local pattern just got broken. That's because we referenced the direction as a part of the wheel. But I guess we don't have to do that. We can reference the this edge instead. All we're looking for is the direction that goes across there. Awesome. I'm OCD, and I see this madness. I could try to rotate the wheel, or I could make just rotate the shaft, and so I'm going to rotate the shaft. Okay, there we go. There we are. Now our there's a bearing that's going to be set inside the wheel on just this side, and then we're going to set another bearing, just a second bearing on the sprocket itself. So let's insert a bearing. Mechanical bearings, bearing hex 1/2 inch. We'll take that and this, make them concentric. We want to make sure that the flange is going to be on the outside and this base gets tucked inside the actual support of the bushing. So I'm going to flip it around, of the sprocket. And then that face and that face are going to be flush against each other. Now there's another cool thing that you can do here with, currently this bearing can spin around still. It's not defined. You can actually take a concentric and you can lock rotation. And wherever it is, it just arbitrarily locks it in place and it won't be able to rotate. That's handy sometimes when things really don't matter. But since I'm OCD, I'm going to make that face and that face parallel to each other. That way it lines up very nicely and we don't have any CAD interferences. I'm tired of looking at this 4.57. I'm just going to turn that off. These are annotation views. You can turn on and off annotations. Okay. Look at that. This is, I'm going to turn off annotations again. There we go. That is a really nice looking wheel. Now, next thing is let's insert the rest of those wheels. You might think that we want to linear pattern this one wheel to the next, to the next, to the next, but I remind you that if we look at it from the side view, this wheel is actually hovering above the ground. And this one's touching the ground, and that one's touching the ground, and this one's hovering above the ground. So it's actually not in a straight line. I noticed that this wheel is a little bit, the tread is set as a 1/4 inch, not 0.2. I'm OCD, so allow me to correct that. There we go, much better. So now what we're going to do is just insert a second one of these. It's not going to be too much work. Whoops. That would be inserting just the shaft. I want to insert the entire wheel subassembly. There we go. So now I've got a complete separate new assembly. I'm going to make the inside of that hole concentric to the inside of that hole. I'm going to make the top plane of this to the top plane of that. Not coincident because they're not the same height. I'm going to make them parallel. This one's higher, this one's lower. And then lastly, I'm going to make the right plane of this one coincident with the right plane of that one. They're in the same robot side to side location. That's fine. But there you go. Look at that. Now we've placed that second one. Let's mirror this to the other side. So on our front mirror, we're just going to click, click. Look at that. Now we've got 4 wheels on this side. And then in our right mirror, we want to move those to the other side. We actually won't, let me just show you here. When we enter the right mirror right now, look at that. These guys don't appear anymore. We just see those. That is because the right mirror occurs first and then the front mirror occurs. If we want to, we can put the right mirror underneath the front mirror. That way the right mirror can reference the front mirror, but the front mirror can't reference the right mirror. That's the hierarchy thing. What comes first? The front mirror comes first in this case. We just rearranged it. Now we can click every single one of these like that. and it'll mirror it to the other side. Now we've got all of our wheels. But we're not quite done yet. It's looking really good, but we're not quite done yet. Because as soon as my computer starts thinking, there it is. Look at this. This has one sprocket on the left, this has one sprocket on the right, this has two sprockets. All of them have two sprockets right now. So we're going to create, before I gave this complicated, long-winded description of how we're going to do that really elegantly, we might be tempted to replace these with save as modeled versions. Just save this component as and delete the right-hand sprocket. But that's not the most elegant solution. There's a better way of doing it. Check this out. This is your tree tab. This is your property manager tab. This is your configurations tab. This is what we're looking at. This is for appearances if you wanted to know too. But configurations is what we're going to be looking at. This is the default or the go-to. This is the standard that has all of every single component visible. Let's just rename this for simplicity to 2-sprocket, because we have 2 sprockets in this view. And we're going to create another configuration. Currently, it doesn't look any different, but we have to tell it how it's going to be different. We're going to suppress the one that we don't want to see in this version, like that. And we're going to have to create a new bearing. You can't change mates around. You can only, here we go. You can only suppress and unsuppress components. But you'll see how why this is awesome in just a second. Doing that. Cool. There's that. That's 1 sprocket. Wheel side. Now when you enter 2 sprocket again, look at that. Look what happens. We essentially have 2 different subassemblies, very, very similar with each other, but they are they're derived from the same wheel subassembly. They just have different conditions, different parts that are turned on or turned off. Suppressing is essentially hiding, but it actually it's almost like it's between hiding and deleting a part. It's like deleting a part, but you can bring it back. So it's like taking it out of the assembly, as if you pushed it off the table. But you can always pick it up off the ground again. Now in this 2-sprocket configuration, currently I still have a when I added that second sprocket, that second bearing, it's here still. I don't want that to be present in the 2-sprocket configuration, only in the 1-sprocket configuration. So you can see how it will turn off that bearing and turn that one on. Great. So now, oh goodness, it's taking a long time to think now. I should save before SolidWorks crashes. It's going to happen sometime soon. I can feel it. We've got one more configuration to add. So we've just done this one, the wheel side. Now let's do this one, the one that's far out of the wheel. We don't want to have, just make these 2 the same instance, because then our chain would have to bend to stretch and get over here. And when chain has to bend out of a single plane, it ends up grinding on the teeth of the sprockets. and that significantly decreases the lifespan of the chain and the sprocket, and ends up costing you in efficiency and makes your drivetrain drive very weirdly. But what we're going to do is we're going to add another add configuration. This is going to be 2 sprocket, I don't know, plate side, not wheel side, plate side. Good. And we don't want to see that. I think what we're going to have us do is just put a few spacers, like a few washers that go inside between these 2 plastic pieces. I'm not going to bother modeling those. That'd take a little bit. That's extra time. You can put that kind of level of detail in if you want to. As you're building this for mechanical, to be looking at all these subassemblies, at some point it would be good practice to put all of those, every single one of those kind of details in place. But now let's go back into our assembly. Uh-oh, hasn't read our mind yet. Look at that, we've still got 2 sprockets up there when we're expecting 1. But check out what happens now. When you click on this, you get this drop-down menu. These naming schemes should look familiar. You can say, I want this to be the configuration on the wheel side. Click the check mark, and look at that. It changes the configuration, but leaves these guys intact. Yep, it's also left this one intact too, the one that's mirrored across the other side. Now let's change this to the plate side. Perfect. You know, I'm feeling a little bit lazy. I want this to be mirrored across there for me. So what I'm going to do is on my right mirror, I'm going to deselect these guys. And then reselect them. And then it'll pay attention to the no, I don't want to do that. Then it'll pay attention to the actual configurations that we've set on there. There we go. So now you can see here, this one doesn't have the center. This one doesn't have the outside, and that's looking really good. Fantastic. 2 more things to do, and then I think we're done with this chapter here. Let's add the sprocket that is driving all of these. So let's go ahead and insert, browse for a sprocket, 1/2-inch hex, 16 tooth. There it is. We'll just insert 1. Very nice. We will make this centric with that. Bring this back. Make that and that parallel to each other. We'll make these the two front faces of the sprocket should be aligned with each other, like that. Then we'll need a second sprocket, right? Because we can see here, this is going to drive that, and that's going to drive that. This is going to drive this, and this is going to drive that. So we're going to need to add the second sprocket. So there it is. And this is going to be in line with that. Concentric with that. And don't want to forget, we can still spin. So parallel with that. Look at that. The designers here at Vex Robotics or Andy Mark and Andy Mark, they're all very smart people. They've made the width of this hub the correct distance for spacing chain. So you can see here when they're aligned, the hubs won't, the hubs make sure that you can't grind the chain together. So that's a very intelligent design, makes our job designing the robot in just 6 weeks that much easier to not have to think about these things. Chain is a very, very tricky beast, especially when it's going under all that stress. It can get very tricky if you don't handle it properly. Now, the last thing that I want to do is talk about this shaft. I mentioned this way early on in this episode. I was saying that I really don't know how long this shaft is, and I don't. Right now I've set it at arbitrarily 5 inches, but it's a bad thing if you have your shaft going outside of your frame perimeter. Your frame perimeter can only be breached by minor protrusions by 1/4 inch. That's just enough for bolt heads. So these are fine. If we have a thick bolt head, that'll be okay. That can protrude, but if it's protruding, an extra inch, that's not okay by first rules, first regulations. So check out this trick. What I did was I replaced the surface. The surface is like a skin that's not actually solid, so I just deleted that specific skin that was for the shaft, and then I just extruded a hexagon and extruded it to a random number. But now I know that the length of this can be an offset from surface. Maybe just poke through 1/8 of an inch. Just poke through enough, right? What I think I would like to end up doing in the future, and we'll get into more of this detail next time, is add a bearing block that will accept this shaft and support the shaft, this far cantilevered end of the shaft. This plate should support this cantilevered end of the shaft. That way, when the drivetrain is going under crazy stress loads, it's not bending the shaft down and compromising the chain tension. So it's going to be a good practice to mount that bearing on a bearing block, which means that it's just not rigidly defined as a circle that's cut inside this frame plate. It'll be a secondary plate that can be moved around by hand, and after the robot is assembled to this point that we see here, we'll rivet in where the bearing is going to go. So in essence, it eliminates the problem of having to very precisely mount our gearbox. We can mount it kind of quick and dirty, and then mount our bearing wherever it should fit, wherever the shaft ends up. And it's just a nice way of very quickly doing a great mount job. Next time we'll go into some more detail on refining this drivetrain a little bit more. There was more detail that we need to add before it would be manufacturable and stunning on the FRC field. There's more detail that we want to be adding here, but we covered a lot of good stuff today: configurations, equations, global variables, a lot of good stuff. And all that really makes for a powerful robot design that's really fast to make changes to. And after you get the sense of how all these relations are coming together, and you know what's making decisions and what's just following what's been decided, a hierarchy of logic, very similar to how programming, working in programming works. You can really make the entire 3D CAD model work very well together and adapt very well to new changes. So that's that, and I look forward to next episode.